Bivariate random variable plays very important role in probability distributions. In bivariate random variable, we have two cases. One is discrete random variable case and another one is continuous random variable case. In this video, we are going to learn about bivariate random variable in continuous random variable case. Let's start. Distribution function. For this, here let x comma y be two-dimensional continuous random variables or bivariate continuous random variables having distribution function is a real valued function. That real valued function is capital F of x comma y, and it is defined as probability of capital X less than or equal to small x, capital Y less than or equal to small y, for all x comma y are real numbers. Sometimes the distribution function f of x comma y is also be written as f suffix capital XY of small x comma y. Joint probability density function. In shortly, we call it as JPDF. Means joint probability density function. X comma y, we call x comma y as bivariate continuous random variables or two-dimensional continuous random variables. Assuming all values in the real number line or real line capital R in the region capital R of the xy plane, then a function f of x comma y, means here small f of x comma y, defined such that capital F of x comma y is equal to integral minus infinity to x integral minus infinity to y f of x comma y dy dx is called, this notation is called joint probability density function in two-dimensional case or in bivariate continuous random variable case. The properties satisfies the joint probability density function is first property f of x comma y is greater than or equal to 0, means non-negative property. Second one is integral minus infinity to infinity, and two-dimensional case means integral minus infinity to infinity f of x comma y is always is equal to 1. Now, marginal continuous distribution function. What is marginal continuous distribution function? Let x comma y be bivariate continuous random variable or two-dimensional continuous random variable having f of x comma y. What is the meaning of f of x comma y? It is joint probability function. having f of x comma y as a joint probability function. Now the marginal continuous distribution function of the continuous random variable x is defined as capital F of x is equal to probability of x less than or equal to small x. Here, what is the meaning of x less than or equal to small x? Means it is also, because it is in a two-dimensional case, we have probability of x less than or equal to small x and y less than infinity. So there is no value for y in marginal case. Here we are going to write integral minus infinity to x. This is in x plane, and in y plane case is minus infinity to plus infinity. F of x comma y dy into dx. This is marginal distribution function of x. Similarly, marginal distribution function means continuous distribution function of the random variable y is defined as capital F of y. It is equal to probability of capital Y less than or equal to small y. So because of this is two-dimensional case, we have now probability of x less than infinity or and y less than or equal to small y, which is equal to integral minus infinity to infinity in x plane, and in y plane it has minus infinity to upper limit as y here. F of x comma y into dy dx. This is called marginal distribution function of y. Now, marginal probability density function. In another way, we call it as MPDF, marginal probability density function. Here, let x comma y be bivariate continuous random variables, or we call another name x comma y as two-dimensional continuous random variable. Capital F of x comma y and small f of x comma y. What is the meaning of capital F of x comma y? This is distribution function. And what about the small f of x comma y? This is joint probability density function. Then the marginal distribution function of the marginal distribution function of x and y is denoted by capital X and capital Y. Already we seen in our definition. Now we have marginal probability density function of x. Marginal probability density function of x is given by small f of x is equal to integral minus infinity to infinity f of x comma y into dy, which is also can be written as d by dx of capital F of x, means capital F of x. So this is distribution function. Distribution function with respect to x derivative చేస్తే small f of x వస్తుంది, ఆ వాల్యూ దీంతో ఈక్వల్ అవుతుంది. And the marginal probability density function of y is given by f of y is equal to integral minus infinity to infinity f of x comma y into dx. Means it can be also can be get by the value by the formula d by dy of capital F of y. This is about marginal probability density function of x. This is of marginal probability density function of y. If here x comma y are independent, if and only if f of x comma y is also can be written as f of x into f of y. Now conditional probability density function. Here let x comma y be two-dimensional continuous random variables with joint probability density function f of x comma y. Now the conditional probability density function of x given by capital Y is equal to small y is defined as f of x by y. Already we know about conditional event in our Bayes theorem. So f of x by y means we are going to find the conditional probability density function of x given y is equal to f of x comma y by f of y. It is the formula for conditional probability density function of x given y. Here f of y the marginal density function of y. Similarly, conditional probability density function of y given capital X is f of y by x. It has the formula f of x comma y by f of x, where f of x is marginal density function of x. Clearly, the denominator values are always greater than 0. Here f of y greater than 0 and here also f of x greater than 0. And we have some properties on that. F of y by x greater than or equal to 0. F of x by y greater than or equal to 0. F of or integral minus infinity to infinity f of x by y dx is always is equal to 1. Similarly, integral minus infinity to infinity f of y by x dy is always is equal to 1. Conditional probability density function satisfies the properties number 1. The conditional probability function of y given x is always non-negative. Similarly, the conditional probability density function of x given y is always non-negative. Third one is integral minus infinity to infinity f of y by x with respect to y means dy is always is equal to 1. Similarly, integral minus infinity to infinity f of x by y with respect to x means dx is always is equal to 1. Now, the cumulative distribution function. What is cumulative distribution function? Here, x comma y be two-dimensional continuous random variables defined as capital F of x comma y is equal to, already we know about that probability of capital X is equal to small x and capital Y is equal to small y. Capital F of x comma y means it indicates probability distribution function. So it has the formula summation, two-dimensional case means summation t less or equal to x and summation s less or equal to y. Probability of t comma s. If x comma y are means bivariate random variable, this is a discrete random variable case with JPMF P of x comma y. So, cumulative distribution function for discrete random variable is given by f of x comma y is equal to P of x is equal to small x, capital Y is equal to y is equal to the formula summation t less than equal summation t less than equal to x, summation s less than equal to y, P of t comma s. This is only for discrete random variable case, cumulative distribution function. And similarly, cumulative distribution function for continuous random variable case is P of capital X less than equal to small x, capital Y less than equal to small y is equal to, so in continuous case we are using integration symbol minus infinity to infinity and minus infinity to infinity. Here we are using two integrations. Why? Because it is in a two-dimensional case. F of t comma s with respect to t and with respect to s. This formula can be used only if x comma y is continuous random variables with JPDF means joint probability density function f of x comma y. And here conclude that cumulative distribution function has two formulas. If x comma y is a discrete random variable, we have one formula, and if f of x comma y is continuous random variable, we have another formula. In addition, we have some properties. Those are, first one is cumulative distribution function capital F of x comma y is always lies between 0 to 1. And second one is capital F of infinity comma infinity is equal to 1. Capital F of minus infinity comma minus infinity is always is equal to 0. Third one is probability of a less than x less than or equal to b y less than or equal to d can be written as f of b comma d minus f of a comma d, and probability of x less than or equal to b where y lies between c to d is equal to f of b comma d minus f of b comma c. And last property, fourth one, is probability of and y lies between c to d. Then we have the formula capital F of b comma d minus capital F of a comma d minus capital F of b comma c plus capital F of a comma c. This is about bivariate random variables definitions. Thank you.